Hello, Hackdonar peeps. I am first of all very thankful that you decided to stick around with my blockchain and to figure out what it is about. So let's just get started. I am Zvezdin Besarabov. I am a second year computer science student at University College London, and I'll be talking to you about smart contracts, blockchain, and Ethereum, and essentially how to code them. So this blockchain will be mostly practical. So most of the time you'll be spending writing code yourself. With that said, I'll have to give you some base theory, but I'll try to keep it to an absolute minimum. Also, sorry if my if my screen is flickering. I don't really have an easy way of fixing that right now. Okay, so what about my background in this topic? Well, I've been working with blockchain for the past about 4 years or so. I've been working on a couple of research projects in this area. So most importantly, I was designing a blockchain network for distributed machine learning, as well as back in 2017, I created a university course back in Bulgaria, my home country, on that topic of essentially smart contract development. So that was a 3-month course from January to March 2018. That had about 200 students, which I was very happy to have that. And yeah, so this entire lecture today will be essentially a best tips summary of this entire course. And in fact, at the last part, I'll give you a challenge exercise that was actually given to the students of my course to do for a couple of weeks as a project. So it's going to be interesting. Let's just get straight into it. So what's a smart contract? Well, in essence, a smart contract is just like any computer program, except it has a couple of extra features. So smart contracts are trusted, which means that you can trust that if a smart contract does something, you can trust that the only way that it did it is because its code said that it has to do that. So what I'm saying is nothing can interfere with the execution of the code. Whatever the code says is what happens, and no exceptions. That's really important. That's actually the biggest selling point of a blockchain, and in particular of smart contracts in this case. And you will start to understand why that's so key and fundamental a bit later. Smart contracts are also incredibly easy to develop. In fact, we will start by essentially after about 20-30 minutes, you'll be able to write one yourself today, right now. So yeah, it's pretty cool. But they also have a couple of side effects. So the most obvious thing is that they're very expensive to operate with because of the nature, because of the way they have to be trusted. They are also pretty expensive every time you want to do some action with them. So what I'm saying is you really have to make sure that you're benefiting from the trust of a smart contract, because otherwise the costs might be way too much for you or for your users. And also, another really important point, and I would say that this is the most important point, is that smart contracts are extremely risky. The way they work, in order to provide the guarantee that whatever the code says that happens, that implies that once the smart contract is uploaded in the blockchain, nobody can change the code. So you get this guarantee that it works exactly as the code says. But it also means that if you leave a computer bug in it, then you're gonna have a pretty hard time figuring out, trying to fix it essentially, because you can't. You won't be able to fix it. And we've had way too many cases in the past where people have developed smart contracts. In fact, the creators of the Ethereum, essentially the programming language which is used in Ethereum, those creators created a smart contract to crowdfund the development of Ethereum, and it failed big time. In fact, it became the largest crowdfunding campaign in history, collected a couple tens of millions of dollars at the time, and then somebody just found a bug in it, and they just completely withdrew all of the money out of it. So it's risky business, which is why understanding it is very important. And here I also refer you to my previous workshop about blockchain theory. You don't need to have attended my previous workshop to understand this one, but if you are looking to honestly integrate blockchain into a project that goes beyond the hackathon, then understanding blockchain theory is extremely important. And so I will highly recommend you to check out the workshop recording. with that said, let's just get straight to the point. So let's just take a look at one example smart contract, and let's try to execute it. Let's try to see what's up with it. So what I'll be demonstrating here is essentially as simple as smart contracts get. So this will be a very simple contract that allows us to store one number in it and allows us to get that number. So let's just get straight to the task. So in order to do this, we need to take a look at this online ID environment called remix.ethereum.org. Pay more attention in this demo right now, because you'll be using exactly the same environments during your exercises. So once you open Remix, that's essentially an online code text editor plus compiler plus a way to execute contracts. So it's essentially your all-in-one place tool to play with blockchain stuff. Cool. So let's just open this contract that I just showed you. In fact, this is one of the default contracts that come with every time you open Remix. So if you guys open the same web page, you'll see exactly the same thing. So first of all, what is a contract? What does this contract keyword mean? Well, if you have done object-oriented programming or anything related to Java, essentially, a contract, you can think of it as an analogy to a class. So it simply defines everything that can happen to one instance of your contract. So that means that your contract has some data that gets preserved indefinitely. So this data stays there forever while the contract exists, which is forever. And then you have some functions which can operate with your data. So these functions may store some temporary data inside them, but after they execute, the only thing that's left after them is whatever changes there are to the original data. And that's essentially it. So in this case, the only data that our contract is storing forever is, well, a particular number, which is of type UN256. Now, fun fact, in Ethereum, by default, integers are 256 bits long. This is 32 bytes, not 32 bits. This is a humongous number, and the reason for I'll get to why that's the reason a bit later. But what that means is that you can store humongous things in these contracts. And in many cases, using a smaller integer that's like 32 bits, for example, is less efficient than using a 32 byte one. So okay, so we have that number up and running. What do we have here? So we have a function that takes an argument, a number, and simply assigns that new number to our state number. So that's pretty much it. So that's so this is a function that allows anyone to allows people to change that number. Good stuff. And we also have another function which simply returns that number. So it allows people to read it. Cool. So let's just run this contract. Let's just play with it and see what's going on. So if you notice on the left hand side, you will see a compiler. So we can compile it, and it compiled without errors. That's good stuff. So once it has compiled, we can go to the deploy and run transactions tab, which is where we get to essentially simulate one blockchain to actually run this thing. Because, well, smart contracts are only made to be executed in a blockchain environment. You can't really do that without a blockchain. So, but you still need to be able to test them locally, because, well, you need to test stuff before you put them in the real blockchain. So what Remix allows you to do is it allows you to start a simulated fake blockchain on your local machine, and this simulated fake blockchain is going to execute your smart contract. Now the details of this are hidden away so that it just works, but it's just cool to understand that an actual virtual machine is started here. Cool. So we're not gonna change any of the settings here. You don't really need to understand them at this stage. We'll just go straight down to this selector for contract. So we're gonna select this contract, which is, well, the contract we just compiled, and then we're gonna click deploy. So what happens is down here we see one instance of our storage contract. So that's just one particular contract being created and being deployed in the blockchain. and it has two buttons, respecting to the two functions we have in our contract. So let's just try and execute them. So I'll just type in the argument, let's say 10. I'll click store, and then I'll click retrieve, and I'll get the result 10, which is, well, exactly what we expected it to do. So what happens when you click these buttons actually is that Remix sends a blockchain transaction to your simulated local blockchain, and we can see the details of that down here. In fact, it says transaction to storage pending, and we get to see a ton of details about this transaction because, well, this is an actual blockchain transaction. It, of course, in our fake blockchain, but nonetheless. Yeah, we don't need to understand these details, but it's cool to understand that there's more to it than simply running a function. Cool. A fun fact about a contract is that, well, in order for them to provide the guarantee that they just work with and that nobody can change their code, they need to work in a blockchain. Now, in order to work in a blockchain, they need to be replicated around literally every computer running this blockchain. So a side effect from this is that, unfortunately, you cannot have private data stored in a smart contract because there is no way to keep it private. The only way that a smart contract is a smart contract is if it gets copied around everywhere, including its data. So anything put in a smart contract must be public. And even if you don't even if you don't write a function that says, let's say if I remove this retrieve function, that doesn't change anything, because in order for different computers to be able to execute this smart contract, they need to know what's the state of the smart contract. So you can't really hide anything. With that said, there's also a notable difference between these two functions I want to point out here, is that one function changes data. So one function is like a full blockchain transaction because it changes stuff. So it's like normal. No, a normal transaction, okay? Whereas the retrieve function, it only reads data, so it doesn't change anything about the smart contract. It doesn't change anything about the blockchain. So in fact, we don't really need to send a blockchain transaction to execute the retrieve function. In fact, if we are a computer running the Ethereum blockchain, we already have access to the state of the storage contract, because this is the requirement in order for us to be able to even run the blockchain. So our computer already has all of the data it needs to execute this function. So it can just easily do that without submitting a full blockchain transaction. Now, a nice bonus from this is that, well, if we're doing something locally for ourselves, we don't need to pay for it. So there are no transaction fees and there are no limits and nothing like that. So that's pretty cool. And the way you declare that one function doesn't change any state is by putting the modifier view on it. Okay, that's about it for the storage contract. Cool. Now, let's take the decentralization analogy and figure out essentially where's the value of smart contracts coming from. So, in the case of a normal financial transaction, let's say, you would usually have to go through a bank. So, a bank tells you that you have X amount of money, and a bank tells you that you have the right to send X amount of money to somebody else. So the bank is essentially a completely centralized controller, and it's essentially just like that when you're trying to execute computer programs. So if a computer program has multiple users, it is usually stored on a server. So users send some data to this server, the server decides what to do with this data and sends the result back to the user. And this has to be the case because multiple users may be using the server at the same time. So you want to have one place where the data is kept, right? So this is how it works traditionally. But with blockchain, it's not really the case. In fact, with blockchain, due to some of the things I already mentioned in my example, actions can happen independently of centralized authorities. So in fact, if I want to send some money to somebody else, I can easily do that in a blockchain, and I have pretty much the guarantee that I will be able to do exactly what what I think I'll be able to do, and there is nobody in the world has the power of stopping my ability of sending money to somebody else. And it's essentially a pretty similar thing with computer programs as well. So let's take the example of a voting system. So most likely, if you see something like this, like some ancient looking online voting system, you really wouldn't want to use it, right? Because you don't really know who is running it, and essentially whoever is running it has access to the votes which have been casted. So how can you trust that the voting system is fair? Well, this is essentially where Ethereum comes in, and it allows you to run pretty much any computer program in a trusted way, such that, well, like I said, only the way it code says, only this happens. And yeah, it's good stuff. So Ethereum is one of the top cryptocurrencies right now. So one of the two, essentially, usually the second one if you want to count by market capitalization compared to Bitcoin. And it has had by itself a pretty interesting story developing. So around 2015, 2016 is when it started fully. It started having some users. It started its cryptocurrency. It started its smart contracts stuff. And its price has been pretty stale, pretty low, at around between $0 to $3 to $5 to up to 10 or something like that. So this is when I also got introduced to Ethereum, and yeah, it was pretty cool. So in fact, at that time, somebody offered me to pay me about, I think, $3,000 for a job I did for a couple of months, and they offered to transfer this in Ethereum. And I looked at the pricing, it was $10, and I said, oh no, what if it falls back to $5? Then I'll lose half of my $3,000. So I rejected this, and I asked for cash instead. And obviously, you know exactly what happened then. This is what happened with the price of Ethereum. So it went from about $10 to about $1,750. So that's about a 200-fold increase. So my $3,000 would have been in a pretty good state at that time. But yeah, things happen. Anyways, this was around the moment where, well, I was really hesitating to not put any extra money in Ethereum because of this. So I said it got up to $20, and I was like, oh, there is no way it's getting up above this. So I'm not entering with any money. So then it got to $50, and I said again, it's not getting any more up, so I'm not doing anything. and I kept repeating exactly the same thought process until it got to 2K, which is when essentially I said, okay, fine, let me just add some couple of $1,000 in this thing. And I did that, and then it went down by a long shot. So it went down 15 times. 15 times, in fact. So yeah, so rip life savings. So if there's anything you wanna learn from this, is that I may be able to teach you smart contracts, but I'll definitely but I definitely won't be able to teach you how to invest. Cool. So let's just take a look at a much more complicated smart contract example. So this is a pretty simple contract that allows you to cast a vote. So it allows people to it allows you to have a set of voters who have the right to vote, and it also allows these voters to vote for a set of options. And at the end of the voting, it allows you to easily verify who essentially won the election. Cool. And so it looks a bit more complicated, but it's simple. Don't worry. I'll just get to it straight away. So I have it loaded up in this Pastebin link, where I'll just get it. Cool. So what happens here is let's just go over first how this contract stores its state, and then obviously how does it work with this state to deliver the functions we want it to deliver. So first, the contract defines it's a couple of its own structures. So struct is pretty much the same as you would see, let's say, in C++. It's simply data type that contains a couple of smaller data types inside it. That's literally it. It's just a convenient way to combine related data together. So in this case, we want to hold information for every voter because, well, we want to hold whether the particular person has already voted, what they have voted for. Also, our voting system allows people to delegate their vote. So let's say if they have delegated somebody else to vote on their behalf, and we need to be able to mark this. And also, if somebody has voted, if somebody has delegated their votes to you, let's say initially have one vote, but somebody delegates theirs to you, so now you have two votes. So we need to also be able to store that in this variable called weight, which is the number of votes you're allowed to cast. Cool. So this is the structure that we keep for every voter. I'll get to that in a second as to how exactly do we store this for every voter. So we also need to store exactly what are the different proposals for which the people are voting. So for every proposal, every proposal has a name, and we also keep the number of votes that a particular proposal has received. That's pretty much it. Bytes 32 is simply just 32 bytes of data. So it's not like a particular number or a string or anything. It's just some random data that can be put there freely. Cool. So these are our data types, and how do we actually store them? Well, we use this concept called a mapping. So if you've used a hash map or let's say a Python dictionary, this is going to be a pretty similar thing. So it's just a key value pair between a key identifying a particular value stored in this map. So in this case, we want to store one voter structure for every voter. Now in Ethereum, users are usually identified by their address. So this is their publicly accessible identifier. This is what you see when you let's say open a blockchain explorer and you see a transaction from some random number to some random number. Well, these are the addresses of the people. So we want to map people's addresses to their voting structures. That's it, and that's exactly what we're doing here. And because we also have only a limited set of proposals, so let's say like 10, we don't really need to store them in a mapping. We can just store them in a normal array. So that's just a proposal array of proposals. A cool thing about Solidity is that the arrays are dynamic, so you don't have to declare their size when they're created. So that means that here we haven't really specified how many proposals we have, and later we'll just add them one by one, and it's going to work. Cool. Another cool thing we don't really need to be caring about is, let's say in this mapping, this mapping can actually scale as much as we want it to. So possibly it could have 10 voters, it could have 1 billion voters, and that's fine. This is not going to break our smart contract in any way, shape, or form. Because of the way the EVM, the Ethereum virtual machine, is structured, you can actually have there isn't a recurring cost of your contract storing a lot of data. So every time some data is stored, some additional data is stored by your contract, whoever stores them has to pay as transaction fees. But once that fee is paid, you don't need to pay any more for the fact that you have a lot of data. So yeah, this is getting a bit convoluted, but what I'm saying is this is a nice convenience feature that you don't really need to think about how much data you should be storing in this particular instance. Of course, in many others, it completely breaks or makes your smart contract function. So yeah. So anyways, let's continue on. So every smart contract has a constructor. So it's labeled by this, which is essentially the function that is called whenever the smart contract is created. So this is called only once, and this is only called by the person, the address who published the blockchain, who published the smart contract on the blockchain. This is very important, and because we can usually refer to that person as the owner of the contract, as the person who has, let's say, more administrative privileges in operating with the smart contract. For example, in our case, the person who creates the ballot, we want to give them the rights to add extra rights to vote to other people. So let's say that person, they create the smart contract with a set of proposals, but we also want to be able to give different people the right to vote, right? And because of the way smart contracts work, and this is something I didn't mention last time, which I really should, it's really important. Absolutely everybody on the blockchain can execute any function of any smart contract. There is no limitation. What that means is that you have to put custom logic in your functions in order to see whether somebody should be able to execute that function or not. And this is very important. And so if we have a function which tries to give some person the right to vote, which is what we see here, we want this function to only be executed by whoever created the smart contract. Simply because otherwise, if everybody can just add random voters, then this election will very quickly turn into a complete unfair election. And so the way to do this is essentially, if in a function you use message.sender, that gives you the address of whoever is currently executing that function. And because that function right now is the constructor, we know that the only person who could be executing the constructor is the person who created the smart contract, and which is also the special person who has the rights to, who we want to give the rights to to essentially register new voters. So we have this state variable called chairperson, and this is how we remember who they are, so that we can check against this variable later, when we have to. So in the constructor, we also make the chairperson a voter, simply because, well, why shouldn't they be able to vote? And then the constructor takes in an array of the names of the proposals. So we simply want to convert that array into or array of proposal objects, so our proposal structures. So what we do is we simply iterate for every proposal name in the array. We simply say create a new proposal structure that way, and then add it to the proposals array. So let's take a look at that deeper. So the syntax of creating a new structure is this way. So you have the name of the structure, and then in parentheses you have a key value pair for the different values of that structure. So in this case, we store its name, and we initialize vote count to 0 because, well, it's 0. Cool. So let's take a look at how we give people the right to vote. So like I mentioned, we only want the chairperson to be able to do that. So what we do is we have to check whether whoever is executing this function is actually the chairperson. And if this isn't, we want to stop the execution of the function. So the way to do that in Solidity is to use the require keyword. So require keyword takes in some binary check, and if that validity check is false, then it throws an exception. It stops the execution of the contract, and it says it essentially throws an error message. So this is the easiest way that we put extra checks in our smart contract. So let's say that whoever is executing this function is actually the chairperson. So the next step is to figure out if it is possible to register the particular person as a voter. Now first we want to check if we have registered this person as a voter from before, because, well, if we have already registered them and if they've already voted, then we don't want to remove their vote. We don't want to give them the right to vote again. That's just simply unfair. So we have to add these extra checks. For example, we want to take the voter structure for the particular address voter in this case, which is what's given to this function. So the voters was a mapping. Remember, it's a key value pair up here. So the way we access a particular value is by using these square brackets and adding the key into them. So we access the voter structure and we see, has this person already voted? So if they have, we throw an exception because we shouldn't be able to register a new voter if they have already been registered and if they have already voted. We want a fairer election, right? Cool. It could be the case that they actually haven't voted yet, but their voting weight is 0. So that means they have already been registered. They have already delegated their votes to somebody else, and whoever is that somebody else, they have already voted on their behalf. So we also have to check for these checks as well. So in this case, if the voting weight of the particular voter is not 0, then well that is also another indication that says that they have already been registered to vote. So we shouldn't register them again. These are simply additional logical checks for the particular way that we have structured our logic here. I don't want to get too deep into them because that's not really exactly what I'm trying to demonstrate here, which is solidity. But the concept that I'm trying to show you here is that every time something is calling your function, you need to check all of the conditions that must be true in order for you to do the thing you want to do in your function. So because anyone can call this function at any time, we want to make sure it works exactly when we want it to work and nowhere else. So if all checks have passed, then what we do, and this is very convenient for Solidity, so we take the voter struct for the particular voter, which we know hasn't been created yet, and we set its weights to 1. But wait, how did we do that? Because I just said if these checks have passed before that means that this person hasn't already been registered to vote. So how come can we just take the voters mapping and simply access a structure that we have never created ourselves? Remember here in the constructor, in the proposals, for every proposal we had to create a new structure. So why don't we create a new structure for the voter here? And that's something very convenient for Solidity. And that is that every time you try to access a variable which hasn't been created, it gets created automatically with the value 0, with everything inside it initialized to 0. So the moment we access the voters mapping for a new voter which hasn't been ever seen yet by Solidity and by this mapping, what happens is that Solidity goes in, creates a new structure voter and initializes all of its fields to 0, which is pretty convenient because if we want to register a new voter, everything in this structure is 0 except its voting weight, and that person's voting weight becomes 1 because they're able to cast a vote. This is how we want to tell them to cast a vote. So yeah, so this is essentially why this entire function is just one single line. So everything else is just checks whether this function can be executed. So yeah, so Solidity is pretty interesting. I'm going to skip the mechanism of how votes are delegated because it essentially uses a very much of the same Solidity concepts, except that there are a lot more edge cases here to take a look at. It's just going to take more time. So let's just see how exactly people can vote. So well, people can vote for a particular proposal, right? So our voting function should take some identifier for proposal. In this case, that proposal, this identifier will be simply the index of the proposal in the proposals array. So yeah, so we want this function to only be called by voters. So what happens is that first we want to get the particular voter structure from the voters mapping for whoever is calling this function. Remember, message.sender gives us the address of the caller right now, and we know that this will work all the time because even if this voter doesn't exist, it still is going to create a voter structure for us. It's just going to be 0. Cool. So now we have this sender, which is the variable for voter structure, and we can do some checks. So first of all, if the sender doesn't have voting weights, well, that he has no rights to vote. So we shouldn't be able to give them the right to vote. So the function shouldn't be executing beyond this point if the weight is 0. Let's say it isn't. Then it also must not be the case that the person has already voted, because, well, if they voted, then that's not good. So we don't want that to happen as well. Cool. So if these checks pass, then we simply do what we want to do. We set its voted flag to true. We set its vote to the particular proposal it voted for. And also for that particular proposal, we take that particular proposal from the proposals array under that index, and we increase its vote count by the number of votes this person is allowed to cast. Now note that this also implies that they should be able to also cast multiple votes at the same time in case people have delegated their votes to them. So yeah, so this is pretty much it. As you can see, this entire function is also pretty much 3 lines, except for the logical checks. It's incredibly simple, but you just really need to understand how things work here, because if you make the slightest mistake, it's gone. It's gone forever. Cool. So the last 2 functions will be a bit simpler. They don't change any of the data on the smart contract. They just calculate which proposal has the most votes. Cool. So the function winning proposal simply tells us the index of the proposal which has the highest vote count. So that's a pretty simple loop. So we loop from index 0 to the last index in the proposals array, and we take a look at the vote count for every proposal, and we register the highest vote count that we see here, and we also register the index of the highest vote count, and that's it. Notice that this function should return the index of the winning proposal, right? So why do I not write return winning proposal? Well, actually I can do that, but I don't have to do that, because Solidity has this convenience feature up here in the function definition that says returns, and then in the brackets it declares a new variable. So you can think of this as actually declaring a new variable at the start of your function, and then during your function you just set the value of this variable to whatever you want to return, and once your function completes, Solidity automatically adds return winning proposal at the end. So it's just convenient. Cool. And we also have another function to read election results, which is that we have this. So we get the winning proposal, which is again, like I said, the index within the proposals array, and so we get a particular proposal for that index, and we get its name, and this is what we return. So this function simply takes the name of the winning proposal. So yeah. Pretty convenient functions. So as you can see, it was incredibly easy to develop this to that extent. And even though it probably looked more complicated to you because it's new, but after you get used to it, it really isn't. It's pretty simple. You just really need to be careful with everything here. Simply because it's so simple, there's some tiny details as to how this works under the hood that we shouldn't ignore. Cool. So let's just move on with another discussion on essentially smart contracts. So the next thing I want to talk about is I want to shift the topic just for a bit. I want to emphasize the fact that you don't really need smart contracts for many cases where people think they need smart contracts. So let's just think about in which cases do we really need smart contracts? Because in fact, in many cases, the downsides of a smart contract are too high compared to whatever upsides there could be for our particular case. So does the value of a smart contract being executed in a completely trusted environment, does it actually, is this something our product needs? Or is it something like a fancy extra feature that, you know, could be cool, but at this stage blockchains are not scalable or not fast, not cheap, whatever, and essentially our product doesn't get used by anybody. So it really is a must to critically reflect in which cases exactly do we benefit from a crypto contract. So yeah, let's just have a small brainstorming moment here to think about that. Yeah. Can you help me by saying in which cases do you really need a crypto contract? Because it's not that obvious actually. It's pretty generic. Crypto contracts that are just, like I said, a guaranteed way to execute some contract logic, some program logic. That's literally it. So in which cases do you really not do you really need to not trust a particular party to execute your computer program? Let's say if you're playing a game, in many cases, well, playing a game is fine when it's hosted on a server because, well, usually whoever is controlling the game server really doesn't want to ruin the game for everybody else by cheating, by changing some data left and right. But let's say that in some scenarios, game publishers really are doing that. Well, not of course hacking servers, but well, they are doing some uncool stuff, like let's say that they're publishing the game for everybody else, and then after that they're introducing some pay to win feature that people can use, and out of nowhere you used to play this game, but now that the rules have changed and now other people can pay to win against you, and that's simply not cool, right? So in this case, we also have a couple of crypto contract games running on blockchain. Of course, in many cases, they're simply too expensive to play. So in not many cases, in fact, we can benefit from a blockchain game. But nonetheless, it is there. Most of the applications of smart contracts come from the financial sector so far. So it's about managing currencies, about managing payments, supply chain transactions, and other things like that. Let's say voting or consensus related topics, organizational related topics. If you're leading a company, if let's say not if you're leading a company, but let's say if you're part of a team of people, and you don't have a particular boss who is responsible for the team, then what could happen in this case is that you could set a couple of rules that your team must adhere to. Let's say your team must do this, and this, and if they don't do that, they are punished that way, for example. So you can more easily write these rules as a crypto contract that everybody in the team can use, so that you don't really have one particular person who is the judge of what happens. But whenever somebody breaks the rules, this is what the rules say. So yeah, it's a bit of a more complicated example, but I hope that you get the gist of it. And talking about financial examples is where we get, I think, to the most interesting example in today's workshop, which is about, well, how do we actually define a new cryptocurrency as essentially a contract. So this is exactly that I'll walk you through right now. In fact, what I walk you through right now is just like literally 20 lines of code, and this defines a new currency. So it's pretty interesting to understand how does it actually do that. Why is this actually a currency? So let me just walk you through that smart contract. Then we'll get to execute it a couple of times, and it will be cool. So what happens is that we want to provide a currency. So we want to provide the ability that, well, first initially, as we're creating a currency, first somebody has to have money. So money has to be created from nowhere, right? Something has to initially put money in the system, and once this something initially puts money into the system, then whoever has money can send money left and right. So that's the whole idea. And note, I'm using money here but I won't be doing any operations with actual money here. In fact, the only thing that I'll be doing is I'll be shifting some numbers, some integers left and right between some data structures in that contract. So this has nothing to do with Bitcoin. This has nothing to do with Ethers, nothing to do with dollars. It literally has no value by itself. It's just a random integer in some random smart contract. Okay, so don't get confused when I say money. But nonetheless, it's interesting to see why this could actually turn into real currency that people can actually and are willing to pay for and exchange for real money and use it for some stuff. So let's just get straight into it. So our currency has two state variables here. So first, it holds the address of the person who created the smart contract, because we want to, as last time, we want to give them some extra privileges. So in this case, the currency needs to have an initial starting point, right? So we want to declare whoever created the contract as this person called the minter, who has the rights to create some new currency out of thin air. Okay, but only this. So this person cannot interfere with already happening transactions between people. And how do you actually store the balances, like who has how much money, is we have this mapping, this key value pair between a user address and essentially a random integer that simply says how much money they have in our system. So again, we're not talking about real money here. It's just integers. Like there's nothing behind the scenes that moves money around. This is just integers right now. Cool. You should probably ignore this event at this stage. It's not really necessary to understand how the contract works. So yeah. So in the constructor, what do is we simply store the address of whoever created the contract as our minter, and that's it. And so we only have two more functions here. So we have a function to create new money out of thin air, which is called mint, and we have a function to send money left and right, which is called send. So let's take a look at mint. So mint must only be called by the minter. What does it take as arguments is that it takes some particular address to which address the money should be added. It created out of thin air, and essentially the amount of money that should be credited to this account. So first we check that this amount of money it isn't too high. Let's say we have this limit. And if whoever is calling this function is indeed the minter and the amount of money is not too high, then what we do is we simply take the balance of that particular receiver and we add the amounts to it. And notice how yet again, if we don't need to initialize the initial balance of the receiver if we have never ever defines this. The moment we access balances for a receiver which we have never accessed balances before, it just becomes zero. So we can just add amounts to it. So it becomes equals to amount. So yeah, simple things. So essentially what this entire function does is it takes one value in this mapping and it puts some money into it. That's literally it. And the magical function here is the send function. So what happens is that we have this is supposed to be called by any person who has enough money in the context of our smart contract. So we have this. So first we add the receiver to whom we want to send money and the amount and that's pretty much it. And first we need to carry out a balance check. So it must be the case that our balance is more or equal to exactly the amount we're trying to send to somebody else, because well, otherwise we don't really have enough money to send that to. So this must be the case. And if this is the case, then what we do is we simply first negate this amount from our balances and add the same amounts to the other person's balance. So the total money in circulation stays the same, but now this other person has this amount. So let's just play with this for a little bit. So let's just first compile the coin and let's just run it just like we did with the other examples. Cool. So let's just deploy the new coin contract, and we can see down here that we have we have a new coin contract with essentially all of these buttons here. Now, something to note here is that we only defined 2 functions, right? So why do we have these 4 functions here? Why do we have these balances and minter? Well, that's another convenience feature by Solidity, and if we declare a public if we declare a variable outside of a function. So this is a global variable, and we put the public modifier to it. Then Solidity automatically creates a function which is named the same way as this variable is named, and this function returns the value of that variable. So it's a pretty convenient way to create basic getters for variables. So in this case, we can call the function minter, which essentially returns my address. So this here is my address. I can double check this up here in the environment. So in the environment, I have a couple of pre-created blockchain accounts that I can use as identities on my fake blockchain in order to execute this contract. And as the first account and the only account that I have used so far is this one, which happens to also be the same as whatever address is stored in the minter variable. So it just works. And I can also try to get the balance. Let's say the balance of my address. So I simply paste in my address here, and my balance is 0, because well, that's exactly what we expect. It's 0. Cool. So let's just try and create some money. So I want to select this second account. I want to copy this address because I want to make some money and I want to assign it to that account. Okay. So and I come back to the first account because only this account has the rights to call the mint function, because well, it needs to be called by the owner, right? So we paste this receiver address and then we do, let's say, 100. So I call mint on this, and we can see down here that we had a successful transaction, so it actually happened. So now if I get my balance, it's still 0, but if I get the balance of this other address, it should say 100, and it says 100. So now let's switch to this other address. So let's execute some transactions from the name of this address. Let's say that I want to send something to this third account. So I want to copy the address of this third account. I want to switch back to the second account, which still has 100 money in our smart contract, and I want to call the send function. So the receiver is this third account, and I want to send them 20 money. So I click send. So yeah, the transaction has succeeded. So what if I get the balance of my account again? Well, now it's 80. Not very surprisingly. And what if I get the balance of this other account that I just sent money to? Well, now it's 20. So yeah, it literally just works to its most basic sense of being a currency. So why does this actually make value? Well, it really doesn't. So nobody really wants to exchange money for this currency. But let's say that we create a product, we create a startup or some sort of platform that works natively with this particular currency. Then people would actually be willing to actually buy it. People would be willing to exchange real money for this token, for this coin, for this currency. Simply because, well, it is in a smart contract. So that means that people know exactly what the currency supply will be. For example, people know exactly that nobody's gonna block future transactions between people. People know essentially exactly. People can trust that this number in somebody's account means something, because nobody can just create money out of thin air. For example, well, in our case, people, the minter can create money out of thin air whenever he wants. So it's a pretty bad example in the case of making an actually functioning currency. But let's say that we simply remove this function. So we simply don't have a minter. Instead of this, we simply have this. So in the constructor, we simply say that initially the minter has 100 money, and that's it. So there is if we deploy this contract now, there is no other possibility that anyone in the world can create new money in this currency. It's just the total supply of currency of money in this system is 100, and the code doesn't say that it can be changed, so it cannot be changed. Well, actually, there are some cases in which for example, you can exploit some bugs in this code and actually possibly change this outcome in some cases. That's because of integers overflows and underflows, which essentially underlines yet again why you have to be really, really careful with understanding some stuff. So this contract is not perfect. In fact, it needs to be. We need to add some extra safety checks for it to work well enough. But I just used it because it's simple enough for the example. But yeah, understand your stuff, kids. It's important. Cool. So yeah. So this is how we can. A currency is just a currency because people believe it has value, and people can believe it has value if it's stable. If they can either trust the centralized controller of this currency in the case of a bank, in case of what happens in the real world, because banks are pretty reputable. They're not going to start ruining the economy, most likely. They're not going to print $1 trillion and give it to some random person, right? It's the same case here, but we don't really have banks. We just have nothing. So people don't really have to trust anyone. They can just read the contract and they can just understand exactly what they should be expecting. And yeah, that stability and confidence is essentially all you need in an economic system. Cool. So let's just wrap up with a couple of exercises that you guys can do right away. Now that I've shown you some more complicated smart contracts, I think that you should be able, with some googling left and right, you should be able to write a couple of your own. So let's start with a bit of a more basic one. So you should probably be able to do this within 15 to 20 minutes or less, which is a pretty simple counting contract. So we want to have a contract which simply holds a state, which simply holds one counter as a state variable, and that contract has a function which will essentially only increase this counter by 1. But this can only happen if this function is called by the contract owner. Otherwise, it shouldn't change the counter. And there should also be a function to get the counter, so it's simply a way of reading it. And as an additional complication, you should also add some integer overflow protection. So that means try to not add counter by 1 if this is going to cause an integer overflow. And you should also try to do this without hard coding the actual, let's say, maximum value of this variable, or essentially anything related to the size of this variable. This overflow protection should work whether I have an 8-bit integer or whether I have a 256-bit integer. So yeah. So once you're done with this exercise, and I will be very happy if you can message me on Discord with your solution. I can give you some feedback. I can help you out. You can also message our workshop helpers, which are very happy to help as well. So yeah, and for the second exercise, now this is a bit of a more challenge one. So this is actually part of the final project that I gave to the students of my course 2 years ago. So it's pretty interesting. So the whole point is to create a decentralized domain name system. So you know how domain name systems usually work, which is, well, when you enter whatever something.com, then this needs to be this domain name, this string of text needs to be translated to a particular internet address of whatever server you actually need to connect to load that website. So right now the system is very centralized. So that means that there is this one organization which controls essentially what all the domains are pointing to. So everybody needs to trust that this organization does what it will, essentially does what it has to do. But well, that doesn't have to happen. In fact, this is a pretty simple use case for a smart contract. So let's just do that. So you're going to create this contract, right? it needs to provide the following functionalities. It needs to allow people to buy a domain name. Now, in this case, let's just simplify that a domain name is simply any valid string. So it's just some random string. And you should also accept money, but not money in the context of the coin contract that I showed you about earlier, but actual Ethereum money, so Ethereum tokens. So the price of buying one domain name should be 1 ethers. And you should also obviously not be able to buy a domain which has already been taken by somebody else. So I didn't tell you anything about Ether payments in smart contracts. So you should look that up, or ask me if you don't really know where to look. So other than buying a domain name, whoever has bought a domain name needs to be able to change and set the IP of this domain. Now, for simplicity's sake, let's just say that the IP is just some integer. So as a domain which is a random string simply points to a random integer. So for simplicity's sake, we don't really need to put a real formatted IP there. So obviously this method must only be able to be called by whoever owns that particular domain. And as for reading the data, you should obviously have a method to resolve a domain name. So given a string, this method should return the correct IP for a particular domain, or let's say 0 if that domain doesn't exist, or maybe throw an exception in this case. And also, the way money transfers work in Ethereum is that once somebody sends money to a contract, this money gets stored inside the contract. I'm talking about money like Ether money. So a contract is just like any other address on Ethereum, that it can have its own balance in Ethereum. But therefore, you explicitly need to add some logic that takes that money out of the contract if you really want to use it. And let's say that if you don't do that, then your contract becomes a sinkhole. It becomes a hole where people can give money to it, and it has literally no way of getting these money out. So that's not very good. So you need to add this function so that can allow the owner of the DNS contract to simply withdraw the money that has been collected through domain sales. And for simplicity's sake, you don't really need to think about domain expiration timing and things like that. Just assume that once a domain is bought, it stays there forever. So yeah, that's pretty much the challenge right now. Again, I'll be very happy if you can send me your solutions over Discord, or if you don't have a solution, just a question or anything in the blockchain Discord channel, or of course with our workshop helpers. And otherwise, I was very happy to have you guys here. Here are my extra contact details if you want to keep in touch after Hack the North. Otherwise, I hope you have a great hacking weekend.